I hope yesterday's that diatomic molecule problem is almost over. Am I right? Diatomic molecule in its rotational energy, it will have only two quadratic terms. Okay, that's what you need to remember. Suppose if you want to use classical one, you can use equipartition theorem. Classical. Okay, now classical is different. This classical is different. That classical is different. Classical energy level equipartition theorem can be where equipartition theorem can be applied. Okay, and if quantum, what you call, if you wish to take quantum energy levels of rigid rotator, what you have to do, I mean, I think at very low temperature, take only first two term in the partition function expansion, okay, neglecting higher order part, and then do the calculation. Okay, that's what they are expecting. Okay, and if you wish to take quantum energy level and prove something for high temperature, then that also leads to equipartition theorem answer. That's what we found in the last part of the problem, isn't it? That making J continuous and integrating, we got again KBT only, isn't it? Speak up. Just think over it. At low temperature, you have to respect quantum mechanical energy level, but that summation cannot be evaluated. That's why they may ask some approximation question. Okay, and I'm going to pick this one in what you call specific heat of diatomic molecular gas discussion. Okay, speak up. Whatever we worked out, only rotational part. Vibration may also occur, am I right, between those two atoms of the molecule. Okay, speak up. And translational motion is there when you take a gas. Okay, all of them should be taken care. Okay, speak up. Now I think I don't know what we.
We don't have time.
Wait a second. I'll pick this one. I'll just give the hint. I think it's not a big deal. Then I'll move on. Okay. A circular cylinder of height L, okay, cross sectional area A is filled with a gas of classical point particle. Okay, I will just draw it like this. Okay, height is L here. Okay, so cross sectional area A here. Okay, filled with a gas of classical point particle whose mutual interaction can be ignored. Okay, okay, that means ideal gas. Speak up. The particle, all of mass m, are acted on by the gravity. Okay, let G denote the gravity. Usually, so gravity is downward like this. Okay. Now, whenever this gravity comes, you are free to choose this bottom part of this one as a zero potential. Okay. I will explain this one in classical mechanics while discussing that simple pendulum and all. You will have choice of choosing zero potential actually, because potential formalism is not unique. Is that okay? Pick up. Usually that's a usual one. Okay, pick up. That's a very usual one. Pick up. The system is maintained in thermal equilibrium at temperature T. Let Cv, small cv, be the constant volume specific heat per particle. Okay, specific heat per particle. Compute Cv as a function of T, and the other parameters given, universal parameter. Okay, also note especially the result for the limiting case T tends to 0, T tends to infinity. You need to find specific heat in this question. Okay, speak up. Now, how do you write energy of single particle? Px square by 2m plus Py square by 2m plus Pz square by 2m. Okay, only one, that is gravity. I will take this one as this is z axis. Okay, x here, y here. Okay, speak up. By taking this floor xy plane as a zero potential, you can write your potential energy mg into z, isn't it? Speak up. Z varies from 0 to L. How does xy varies? Xy varies across this cross section. No, not 0 to L. I mean, this is cross sectional part. I mean, this is a cylinder now. Okay. Anyway, that doesn't matter. Okay, you will observe that one. Now, this part of the average you already know, equipartition theorem. only this part of the average you need to find, isn't it? Speak up. So that's why that average MGZ, I'll write in a different slide. Okay, the average MGZ. Can I write it directly? 0 to I mean, all other parts will get cancelled actually. It is MGZ into probability of R to R plus dr, P to P plus dP divided by integral of probability. Okay, pick up. But so this will remain 0 to L MGZ e power minus beta MGZ dz. That dx dy integral, that is cross sectional area, isn't it? That is also common in the numerator and denominator. Okay, whole divided by integral 0 to L e power minus beta mgz dz. I mean, after practice only you should write this one, otherwise you may end up with trouble. Okay, pick up. After some practice you can write this one directly. Only these two integral will be left in the whole that average any average value idea. Okay, pick up. Again, this can be written as minus dou by dou beta of, okay, e power minus beta mgz dz divided by integral 0 to L e power minus beta mgz dz. Okay, so this is equal to this is similar to that reef problem actually. Okay, minus dou by dou beta of, okay, log of 0 to L e power minus beta mgz dz here. Okay, speak up. That's equal to minus dou by dou beta of, okay, log of what is this one, e power minus beta mgz into minus mgz. Am I right? Sorry, beta mg. Integration with respect to by, okay, e power minus beta mgz divided by beta mg minus beta mg. Am I right? Running from 0 to L. Minus dou by dou beta of, okay, what is this one, upper limit minus lower limit. I'll take lower limit first by absorbing this negative sign. 1 minus e power minus beta mg capital L whole divided by beta mg. Okay, oh, log I forgot. Log of this one. Speak up. So that will be minus dou by dou beta log of numerator 1 minus e power minus beta mg capital L, okay, minus dou by dou beta, okay, minus minus plus I think. Am I right? This minus log of a by b, okay, log of, I'll write only log of beta plus dou by dou beta of log of mg. That's constant, that will go, isn't it? Speak up. So this is 1 by beta. I'll write it first, okay, 1 by beta plus this one is 1 minus e power minus beta mgl with negative sign. Am I right? This negative sign, okay. So into derivative of this one minus e power minus beta mgl into minus mgl. So three negative sign came. Am I right? Pick up. Total is again negative. KBT plus, sorry, minus mgl e power minus beta mgl. If you wish, you can take it into denominator. Okay, speak. That is better. That is better. When you take it into denominator, it will be e power beta mgl minus 1. Okay, speak up. So this is nothing but average mgz. Okay, total average energy, that's equal to 3 by 2 kbt due to kinetic energy part, px square by 2m, py square by 2m, pz plus kbt, that is 5 by 2 kbt minus mgl divided by e power beta mgl minus 1. Okay, so then specific heat 5 by 2 5 by 2 kb. Okay, speak up. So plus what is this derivative? Okay, wait a second. I'll write like this. Minus 1 by kb t square dou by dou beta of, okay, minus mgl by e power beta mgl minus 1. Can I write like this? I mean, only this part. It is actually temperature derivative. Temperature derivative is converted into beta derivative like this. Just recall. This part again, I will not do beta derivative. I have already written in terms of temperature. Is that okay? Speak up. So now this is nothing but 5 by 2 kb minus 1 by kb t square plus mgl, okay, minus 1 by e power beta mgl minus 1 the whole square into derivative of this one with respect to beta e power beta mgl into mgl. Okay, speak up. So that is equal to 5 by 2 kb minus mgl whole square. I will balance that kb here somehow. Okay, speak up. Kb, so that I can write kbt the whole square. Kbt the whole square is nothing but beta square. So that e power beta mgl whole divided by e power beta mgl minus 1 the whole square. Okay, speak up. Now, so as temperature tends to 0, beta tends to infinity, or beta mgl tends to infinity. If it is like that, you can neglect this minus 1. Isn't it? Speak up. Then this CV, that's nearly equal to 5 by 2 kb, okay, minus kb times this almost 0. Am I right? Denominator power 2 actually. Okay, speak up. I mean, I will write this one. Okay, speak up. I will write one more time. One more CV, just nearly equal to 5 by 2 kb, okay, minus kb mgl the, because this part should be practiced. Other part, I mean, you should do it very neatly without any mistake. That's it. This part requires some what you call uh, speaker practice. Okay, this minus 1 can be neglected. E power minus 2 beta mgl. Okay, that's why e power minus beta mgl will remain. As this tends to infinity, even though beta square is there, this will drag it to 0. Speak up. That's why. So this is nearly equal to 5 by 2 kb. You are trying to give some physical interpretation for this one. Am I right? At very
Is infinity only in
in other one, not here, because this one of the kb got added. Okay, yeah, that's right. Is that okay? For t tends to infinity, t tends to infinity, beta tends to 0, or beta mgl tends to 0. Am I right? So then what you do, you take first two term in this expansion. Okay, speak up. So CV 5 by 2 kb minus kb. I'll write beta mgl the whole square into, so e power minus beta, sorry, not minus, plus, am I right? E power beta mgl. Okay, when it tends to 0, it will tends to 1 actually. In the denominator, take two terms. Okay, 1 plus beta mgl. Okay, in the denominator, take two term because this is very small. Okay, speak up. Don't make it what you call 0 here. Okay, speak up. Minus 1. I mean, because this will get cancelled actually, isn't it? Pick up the whole square. Don't forget whole square. Now this got cancelled. I mean, you approximate it is e power 0. So CV, that's nearly equal to 5 by 2 kb minus kb. So CV, that's nearly equal to 3 by 2 kb. It looks like only kinetic energy part exists, isn't it? That means at very high temperature, as you increase the temperature, your what you call kinetic energy will increase actually. Am I right? Particles are there only. I mean, in the region of length L. I mean, potential energy is not increasing considerably, isn't it? I mean, it can't go very high height. Okay, speak up. But kinetic energy, momentum, it is gaining, isn't it? Speak up. Because of that, only kinetic energy looks like appreciable at very high temperature. Okay, speak up. So do these things carefully. Let us do this one. I think I can solve all of them. Okay, I'll try. Oh, if we crop, something will happen to this. This is okay. So system is composed of large number of non-interacting classical particle moving in two dimension, which individually obey Hamiltonian like this. Okay, speak up. This is the Hamiltonian of the system. And system is in connected to heat bath at temperature T. Probability of finding a particle within a radius r from the origin. That means you need to go for spherical polar coordinate, not spherical polar. Plane polar, because it's a two dimension. I was trying in a spherical polar actually initially. Okay, speak up. So it is two dimension. Okay, speak up. In two dimension, or by seeing the Hamiltonian, you should quickly say it's a particle in two dimension. Okay. Now in two dimension, what he is saying? Speak up. Suppose if you take two dimension, x y here, probability of finding the particle within the radius r from the origin. Am I right? Probability of finding the particle in this region. That's what he is expecting, isn't it? Speak up. Now, how do you do this one? Speak up. So you know probability of finding the particle from r to r plus dr, irrespective of momentum. How do you do this one? Irrespective of momentum, or I'll write the actual probability of finding the particle from r to r plus dr, or I will write like this. Pick up. Yeah, I'll write this one. Probability of finding the particle from r to r plus dr, p to p plus dp. Okay, speak up. That we have written rho of r comma p, d square of r, d square of p. Why? Two dimension. Okay, that's equal to constant into e power minus beta. Okay, I'll write p vector square by 2m. Okay, this contain px square plus py square into d square of p into e power minus beta. Okay, speak up. A half m omega square. Can I write r square? R square is nothing but x square plus y square. R means this plane polar coordinate r. Okay, speak up. Into d cube of, sorry, d square of r, isn't it? Speak up. Now, in this probability, if you wish to make it irrespective of momentum, probability of finding the particle from r to r plus dr, what would you do? Integrate with respect to momentum. That will give you one more constant, isn't it? Pick up some c prime into e power minus beta half m omega square r square into d square of r. This is an elementary area on a plane. Is that okay? Pick up. That is an elementary area on a plane. Speak up. Now what you need to do is, okay, you should understand this one first. On a plane, okay, this is theta, this is d theta. So there is a patch of area, elementary area. I'm trying to define infinitesimal area element here. Okay. So this is a area element. Okay, on a plane. I'll take this one as R, this one as dr. Now this is dr. What is this one? R d theta. Speak up. So that's why this is R d theta, R d theta, dr. Okay, pick up. So that's why R d theta into dr, it's an elementary area. We write A in electrodynamics and all, area element, we take dA. Okay, that's nothing but d square of R vector. That is simply dx dy on a Cartesian plane. Okay, so in Cartesian, okay, dA or d square of R vector is simply dx dy. Okay, in plane polar. Okay, speak up. In plane polar, this d square or dA, okay, that's nothing but r dr d theta. Okay, this is what you need to know. D theta. Okay, pick up. R ranges from 0 to infinity, theta ranges from, don't write 0 to pi, it's not spherical polar coordinate. I mean, to span the whole region, you have to vary theta from 0 to 2 pi. Okay, 2 pi here. Okay, speak up. This is what you need. Now, probability of finding the particle from 0 to capital R. Am I right? Speak up. So that is nothing but you have to integrate this one. What is this one? Some c prime into e power minus beta half m omega square r square. Am I right? Into uh, d square of r vector. Okay. You have to find that normalization constant, isn't it? I hope they may be expecting proportionality factor. Let us try to eliminate option. Okay, c prime is one constant. Okay, speak up. I'll take it outside. So now, okay, integration with respect to what? Speak up. Integration where r ranges from 0 to capital R, theta ranges from 0 to 2 pi. Theta ranges from full region. I mean, probability of finding the particle irrespective of theta actually. First you have to make like this. Okay. So that's why theta ranges from 0 to 2 pi. That will cover that disk region. Am I right? Ultimately, this disk region should be covered. Am I right? How do you cover this region? Okay, you have to vary your theta from 0 to 2 pi and a radial distance from 0 to capital R. That will cover this region, isn't it? Speak up. So that's why this is nothing but some c prime 0 to r e power minus beta half m omega square r square. Here r dr d theta. Integral 0 to 2 pi d theta. Am I right? Speak up. That's constant actually. So 2 pi into constant. Okay. So here you can substitute. Am I right? This is a derivative of this one. Okay. Speak up. 0 to capital R e power minus beta half m omega square r square r dr. Okay. What you do? I'll write beta m omega square r square by 2 as z. Okay. Speak up. So beta m omega square 2r dr is equal to dz. R dr is equal to 1 by beta m omega square dz. Okay. So that this probability from 0 to capital R, okay, that's nothing but one by beta m omega square. So 0 to, what I better to do is I better to do indefinite integral, then e power minus z dz by this one. Okay, what is that one? Beta m omega square. That's nothing but minus e power minus z. Speak up. Minus e power minus z. I'll do 2 pi c divided by beta m omega square. Now I will substitute that z value. Minus e power minus beta m omega square r square by 2. Then I will take 0 to capital R. Okay. Otherwise, you need to convert z limit actually. Am I right? Pick up. As r tends to 0, z tends to 0. Okay. As r tends to capital R, z tends to something. Z tends to beta m omega square capital R square by 2. You can substitute this one also. Okay. 0 to beta m omega square r square by 2. You can substitute this one also. Okay. That also works actually. I mean, if you wish to do 2 pi c prime divided by beta m omega square. I'll put lower limit first. Okay. Can you eliminate option with this one? I mean, without that constant? Huh. Yeah. You can option 1. Hmm?
What is the T?
I mean, KB. Oh, where is KB? I think there should be, there might be some type.
So beta is K, 1 by K beta.
Oh, KBT should be there. Am I right?
Or maybe that's tau, sir.
Huh?
Tau.
Wait, one second. Let me. No, I'll check the original question. We will add it. Okay. KB should be there. Beta. 2. Okay. KB should be there. Okay. Yeah. Okay. Try other problem again. Daily we shall pick next two more days. Okay. Problem like that. If possible, evening also I'll pick one problem. Okay. I will share one problem solving video. There are 3 to 4 CSIR net questions, okay, which all requires one idea. They will give the problem in different perspective, but that Hamiltonian, whatever they mention, that will be additive. Energy will be additive, and each of those energy will have same possible values. Okay, then that problem is very similar to n particle system converted into n single particle system. Is that okay? Pick up. But when you read the problem, it looks different. But when you look into the mathematics, okay, that is same as the problem that whatever we have solved. Okay. So other than that, I hope many problem it may require some approximation these things. Okay. Most of the problems are similar. Okay. Pick up. It's a very dominant topic. Start solving this one. Okay. Yeah. We'll meet in the evening.